Previously, we have seen that when the receiver knows the value of CSI, we can define ergodic capacity and the capacity with outage. And when the transmitter does not know the value of CSI, it has to adopt a worst case scenario and has to transmit with a fixed capacity of 26.2 kbps. But when we say to the transmitter that okay, some outage probability is okay to us, then the transmitter can now adopt a higher rate of 191.9 kbps. And so when we expect a little outage probability, the capacity is significantly enhanced. Now what if the transmitter knows the value of the CSI? So that means when the transmitter knows the CSI, so will it send the signal when the channel is bad? No, it will not send the signal. It will only send the signal when he knows that the channel is good, and when the channel is bad, it will not transmit its signal. So that means transmitter can adapt its transmission strategy related to the CSI. So in this case, the capacity of the time varying channel is given by summation over S, where S represents the channel states, the capacity of that state multiplied by the probability of occurrence of that particular state. And the capacity of the fading channel with transmitter and receiver CSI is given by this particular form. Now when the transmitter knows the CSI, let us consider we have two scenarios. We have two states. In state 1, we have the SNR gamma 1 of 20 dB, and in state 2, we have gamma 2 as 5 dB. So in this case, the capacity achieved is 6.66 B, and in this case, the capacity achieved is 2.06 B. So now the channel is in two different states. In state 1, we have SNR of 20 dB, and in state 2, we have SNR of 5 dB. That means in this case, the channel is good, and in this case, the channel is bad. So there are multiple things that we can do. We can allocate equal power to both the channels, and when we allocate equal power to both the channels, we can get a capacity of around 8.72 B when we allocate equal power. The other possibility could be if we only allocate all the power to the channel that has the best state. In that case, we can achieve a capacity of 7.65. That means in this case, we are only interested in the state 1. We are allocating all the power to the state 1 and no power is associated with the state 2. So here we can say easily, it can be observed that when we are using both the channels with equal power, the capacity is much higher than when we are only considering the state where the channel is good. That means it has 7.65. So the first observation is we need to use both the states for the transmission. Now if we try to find out some optimal value of power that is allocated to both the channels, then we will get a capacity of around 8.74 times bandwidth. So this results in that we need to use both the channels while allocating separate power to both the channels. And effectively, if more power is allocated to state 1 and the less power is allocated to state 2, we can somewhat have a higher capacity. So then we have a transmit power P gamma, that varies with gamma subject to the average power constraint P bar. So this is the constraint we have, and then the capacity of this fading channel is given as the maximize. We want to maximize this capacity subject to the power constraint, average power constraint, and we want to optimize the value of power that is allocated to this different gammas. So the optimal power that maximizes this expression is given by this. When gamma is greater than gamma naught, the power allocated is 1 by gamma naught minus 1 upon gamma, and when gamma is less than some threshold, then the power allocated is 0. So when we substitute this expression of P gamma by gamma bar in this expression, we get capacity is equal to gamma naught integral gamma naught to infinity b log 2 gamma by gamma naught into distribution of gamma d gamma. Since gamma is time varying, the maximum power adaptation policy is a water filling formula in time. And this curve shows how much power is allocated to the channel for instantaneous SNR. Gamma t is equal to gamma. And the amount of power allocated for a given gamma is equal to 1 by gamma naught minus 1 by gamma, which is equal to this optimal power. So now the intuition behind this water filling algorithm is to take the advantage of the good channel conditions. So when the channel is in good state, you have to allocate more power and more rate can be achieved. And when the channel is bad, the power allocated is less and less rate is achieved. Less rate is sent over this bad channel. But consequently, subsequently, you have to take advantage of both the channels. And when the channel falls below a threshold gamma naught, then we do not want to use the channel.